Swayam Prabha. Digital India. Educated India.
All right, we get started again. So this second part, we sort of go over again a bit on the time evolution operator and actually start talking about transitions induced by a time-dependent potential, electromagnetic field. And we'd also talk about representations in quantum mechanics, specifically interaction picture, which everybody knows. And we'll also talk about start using density matrices, which is going to be at the heart of our approach. Okay. All right. So as a brief thing, so again, we wrote down this time propagator for a time-dependent Hamiltonian. The problem is also that how do we evaluate it and obtain a time-dependent trajectory for a quantum system? If you recall this kind of complicated looking expression, it's not an easy thing to solve. Firstly, you cannot simply truncate it. You cannot truncate it because it's not a converging series. So you cannot simply truncate it, then you're losing information. Moreover, if I start truncating, you can see solutions could potentially oscillate because of the phase. I don't take into consideration all the pathways, maybe you will never converge and it will start oscillating. This is fundamentally a problem. In fact, this could be a little exercise you could do. You can start kind of take a simple two-level system and write down the Dyson expression, run it on your computer. It will never converge, or it will take forever. Nothing comes up. The order of computational expense is humongous, right? So one could kind of think of some kind of discretization, considering some kind of small time steps, so on and so forth. I have written down some notes on possible methods to solving this time evolution operator, which will be part of the course lecture notes, which you can look at. I'm not going to go into that simply because I don't see the utility at this point in time of that. Rather, I would start directly going into the transitions induced by a time-dependent potential. So, as I said, in spectroscopy, right, your Hamiltonian will always look like this. Very important. It should be tattooed on your brain. This is the thing that we are going to work with. And of course, your unperturbed Hamiltonian is that of, let's say, of material that we have figured out. Then your time-dependent wave function can be expanded in this form, where the time-dependent parts comes from the coefficients. Okay, so basically, to predict the wave function, you need to write down the equation of motion of the CKs, the coefficients, basically this. If I expand this out, right line, equation. Not great on this. basically I want to predict the time evolution. It amounts to solving a set of coupled linear ordinary differential equations, right? Which of the form I'm going to write it here. They're all coupled equations. Expand it out to H explicitly. We have time dependent part, time dependent potential. Simplify further. Expand it out in matrix form. Or cross K T minus cross N C N. These are your coupled equations which enable you to evaluate time evolution under a time dependent potential with matrix elements Kn. Nothing fancy over here, it's all pretty straightforward. And now to solve this, so to solve this, I'm going to make I define and substitute C M of t. I should stay in the boundary. Okay. So so we're going to make a substitution here. Your sum of t is sum b m of t e over minus I e over h cross. Why am I making this reasonably wild substitution? You will see it, especially when we go into interaction picture. So you can kind of see I'm replacing my C case with some B case, but you can kind of see C case amplitudes are kind of the same, and B k of 0 is C k of 0. The only thing is that it has a slightly, the B's has a slightly different complex amplitude. That's all. They're kind of identical. In a sense, what we are doing here by replacing C's with B's is that we are pulling out the dynamical phase part, that is time evolving, at a much faster rate compared to the changes in the amplitude of B and C. So a time evolution is happening, and of course you have certain dynamical phase which is evolving, at the rate defined by the eigenenergies of the state. What I'm doing is that I'm kind of pulling that out simply because I'm considering that any changes to either B or C, time-dependent changes, is happening at much slower time scale than the dynamical phase. Now, later on, we will use a very important approximation called rotating wave approximation, which kind of is linked to something like this. That's why I'm kind of introducing this concept straight away, where again, something is happening at very fast time scales, you're kind of going over the envelope and kind of smoothing it out. Okay, we'll revisit this when we talk about rotating wave approximation. So if I make this substitution, then you will see T cross also simplify this further. Sum n. Okay. Kind of elegant looking equation, I would say. Minus EK. Basically, this equation here is the equation of motion. It's a set of coupled equations that describe the probability amplitude moving through the eigenstate due to a time-dependent potential. Right? This equation basically signifies that. Note that the solution for this is still a bunch of coupled linear differential equations. Mostly the solutions are obtained numerically. We may be able to do better using the interaction picture, which is something that we're going to talk now. So all this is in the Schrodinger picture. Okay. So what do you guys know about different representations in quantum mechanics? Anybody can answer. The wave function, apart from the Schrodinger picture where you time evolve the wave function. And there's also the third representation called interaction picture. It's sort of a hybrid between the two. Right? So in the Schrodinger picture, your state vectors are time dependent, your operators are time independent, mostly. Whereas in Heisenberg picture, operators become time dependent. And in the interaction picture, it's a hybrid representation. It so happens it's the most convenient kind of representation while dealing with nonlinear spectroscopy. Okay, so we are going to talk about interaction picture. Okay, so while talking about interaction picture, again, remember your Hamiltonian is H naught plus B of t. It's always the case. And then we are always using the eigenstates of my unperturbed Hamiltonian H naught as the basis to describe the dynamics induced by V of t. Meaning my V of t is still keeping my eigenstates of my system intact. So this again is a condition where I am in fundamentally a V coupling regime. Think of V of t is the electromagnetic field which is coming, right? The weak coupling regime, my states of my system are not mixing with whatever the perturbation is, meaning that my eigenstates are intact, and any evolution of my system, now I'm able to describe it using the basis set associated with the unperturbed Hamiltonian. Okay, this is a very important consideration because especially when you're talking about materials which are strong absorbers, right? This approximation may break. Okay, so I work, for example, with microcavity polaritons, okay, which are coupling light and matter strongly. You can take a microcavity, sandwich the material in between, then you strongly couple the system, and in that regime, your matter is, your eigenstates are built upon both light and matter components, where this approximation may not hold true. Now, it's a completely different challenge, and it's an outstanding problem in the field of nonlinear spectroscopy, how to treat effectively such kind of interactions in the strong light matter coupling. For the sake of this course, we are going to remain in the weak coupling regime, okay, which means I should be able to write out the quantum dynamics of my system using the basis set of my unperturbed Hamiltonian. Okay, good. So if I mean your H naught is time independent, that is simple time dependence part of Hamiltonian. Okay, so basically, let's say I'm again looking at my time evolution operator, going back to time evolution operator. So let's say I'll set v of t for now to 0. Then my time evolution operator is minus I over h cross simply h naught t, and u naught, of course, t naught is exponential h cross integral t naught t d tau h naught of t. Sometimes you explicitly write out a plus here, which is basically telling you, the plus here is telling you that there's a time ordering here, positive time ordering. So it's kind of explicit. Okay, for a time independent H naught, very easy. For time independent H naught, we know for H naught, which is dependent on space, kind of write u naught t naught as e power minus I h naught e minus t naught or h cross, if you remember, right? So we're kind of in that regime right now. Okay, now I'm going to define something. Now I'm going to define my wave function in the interaction picture. My wave function in the interaction picture, I here represent interaction picture, is basically related to my wave function in Schrodinger picture using the time evolution operator associated with my unperturbed Hamiltonian. So what am I doing by defining my wave function like this? What exactly am the purpose of this? Or more than purpose is a bit philosophical, but what am I trying to achieve here? Look carefully. What am I doing here is that I am sort of removing the accumulated phase in my wave function. So in my interaction picture, I'm removing my accumulated phase because I'm going to multiply by e power plus I h naught blah, 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 which is going to remove all my phase, which is actually dynamical phase. Okay, so what I'm doing here is that I'm removing, removes phase due to time evolution. That's the first thing in your interaction picture. I'm kind of removing phase. Okay, now let's go back. And this is just a definition. I need to go back and put it back in a time-dependent Schrodinger equation and see how this looks like. So substituting in Schrodinger equation, of course, I'm going to start the Schrodinger equation in the Schrodinger picture. So this is my wave function, the Schrodinger picture. So I need to rewrite this with interaction picture, that I can write this. Remember what U0 corresponds to. And if I substitute for H being H0 plus B of t and some reorganization, you will see, I'm not going to do that. Why not? Let me do it. It's fine. I can write this as not t cross H0 plus B of t not I cross simplifying this, and we get cross t equal to what I now call as Vi sin I, where Vi potential, time dependent potential in the interaction picture is now written in terms of the time evolution operators of the unperturbed Hamiltonian. This is my time dependent Schrodinger equation in the interaction picture. Of course, related to the wave function shown in the picture. Any comments on this equation here? What this equation might represent? Interaction potential, the potential in interaction picture. What kind of transformation is that? So I know V of t that is given to me. Now I'm changing it in the interaction picture. What kind of transformation is that? It's a unitary transformation. Unitary transformation using what? Using U0, which is a time evolution operator associated with the unperturbed Hamiltonian. So you're kind of making a unitary transformation into a frame of reference defined by my unperturbed Hamiltonian using U0. Okay, so it's kind of makes you to drop unnecessary factors of the unperturbed Hamiltonian and deal only with interaction. That's the name interaction picture, right? Now, what will be the next question? By the way, I can write this Vi as K. So if I L over I, sorry for my handwriting. the matrix elements in the interaction picture are related, of course, to the matrix element with this phase factor. Okay. Kind of want to talk about one more thing, which is basically, so I have spoken about the wave function. We also need to speak about how the time evolution operator looks like in the interaction picture. So in the interaction picture, of course, again, like the definition of my time evolution operator is that if I given a wave function at t naught, and I want to find a wave function at t, and that is given by my time evolution operator in the interaction picture, right? And of course, my ui is the time evolution operator in the interaction picture will only depend on what? Will only depend on the interaction potential, time varying interaction potential defined in the picture, and that we know is exponential minus I over h cross integral t naught t d tau. So simply be v I of tau, which is the interaction, the potential, time driven potential transformed into a basis, into a frame of reference of h naught. So put a plus here to make sure you have time ordering. In fact, you can show that if I write my time evolution operator in my Schrodinger picture for my entire Hamiltonian, that will be u naught, which is the time evolution operator associated with the time independent part of the Hamiltonian, plus, sorry, not plus, multiplied by the time evolution operator in interaction picture. That's your total time evolution. It's just getting a picture of what time evolution operator interaction picture means. If you also recall what we have done previously, we have defined we found a generic equation of motion associated with my coefficients expanded in the basis of my unperturbed Hamiltonian, CKs. And if you recall that, recall CK of t, K psi of t, short in the picture. Now I can expand this out and I can write this K u t naught psi of t naught K u naught multiplied by ui psi t naught, simply e power minus I k t over h cross k ui psi t naught. That's your ck of t, remember? I will write it in terms of my interaction picture. And if you recall, we defined ck of t to be e power minus I ek of t over h cross bk. We're so smart. And it kind of looks identical in one sense, or isomorphic. In fact, we can now say your bk of t that we have written okay. So this bk's naturally represent your equation of motion in the interaction picture. You're dropping away this fast dynamical phase information, but it's enough to capture. These are the expansion coefficients for a wave function defined in the interaction picture. Cool. Now we have an interaction picture. Basically, what we are doing in the interaction picture is we are dropping the baggage and we are just caring about stuff which matter with the time dependent part of the potential. Dropping away all the unnecessary phase, thus anyway we're not going to measure that, we're not fast enough for that, so we kind of drop it, focus. Okay, questions? Okay, if not, let's go to the last part of today's lecture series and talk briefly about an important concept called density. Have you come across density matrix ever in quantum mechanics? Yes, some people know this. So let's first write out the definition. Note that we are never going to care about the wave function, and we are only going to care about the density matrix of our system. That's why I'm going to define this. So density matrix, which is written in terms of rho of T, is defined as projection operator. Right, that's the definition. So we take the wave function, project it on itself, you calculate the density matrix. So what is the relevance of this? The relevance of this is that if you specify a state, let's say some n, then this quantity is basically representing the probability of finding a particle in n. So sort of a quantum equivalent of probability density. Density, thus the name density matrix. Okay. The cool thing about this is that if I'm trying to calculate, let's say, expectation value of an operator, which, as you know already, is given by this expression, I can show, I can simply do this operation if I know the density matrix. Okay, this can be shown, we'll do it. But this is very powerful, okay? Basically, if I want to find expectation values, trace out the product of two matrices, one your operator, the other density matrix of the system, then you'll find expectation values, which are the physical observables. Extremely powerful, right? Which the previous, this expression is almost impossible to kind of evaluate. But density matrix is something that you'll see is it's more tractable. It's a powerful thing to be able to do that. I'll briefly kind of show the proof of this. It's not, I mean, it's mostly for academic interest. It's not going to be relevant for the course. But something that you need to keep in mind is that if I want to calculate expectation value, then I just need to trace out the product of these two matrices, right? Okay, so how do you prove this? So let's say my proof of this. Like if I take my some wave function, which can be written in terms of coefficients, then expectation value can be written thus. In fact, if I look at the elements, the density matrix, rho of t is actually which I can define nm rho nm is simply elements of your density matrix. Substituting this back into that, the top expression, you will see expectation value A sum over M A mn rho mn t, simply trace A rho. Cool. So if I am able to figure out density matrix, then I will be able to evaluate expectation values of any operator. Basically doing this trace. Okay, but this density matrix also has additional information. What additional information exists? So let's look closely again at density matrix. What you will see is if I look at the diagonal elements of the density matrix, diagonal elements, my density matrix, rho n, this will be Cn star. Which is basically my probability of finding the particle in n state equal to 0. It's the probability of occupying a quantum state. It's given by the diagonal elements. Probability of state. Now let's look at off diagonal elements. Look at off diagonal elements. Cn of t, out. Does this strike a note? This expression? Something we discussed at the very beginning of this class, not this class, the previous class. It's basically a coherent oscillatory behavior of superposition states, also referred to as coherence. So my diagonal elements of my density matrix are going to give me a probability of occupying a quantum state, whereas my off-diagonal elements will give me information about coherence. So if I have, let's say, a two-level system, no external perturbation, okay, what will be the density matrix of that? Two-level system, no perturbation, so no time-dependent potential, no V of t. What will be the density matrix of such a system? What will be it? It's a diagonal matrix. What can be? The two-level system usually, if there's no energies. Exactly. Why should something be in the excited state unless there is something driving it? So everything will be in the ground state, so density matrix will be 1, 0, 0, 0. Now, if, for example, I can come with some kind of interaction, okay, and I could create a superposition. If I create a superposition, then I'll have non-zero off-diagonal elements popping up. Now, how will I go and start populating other diagonal element, which is something we will see. But that kind of is, you can start thinking about how the time evolution happens. So now we have something to bookkeep, just the probabilities and the superpositions, and we don't need to care about the wave function anymore. So as far as what matters are just the probability of occupying quantum state and possible presence of coherent superposition or coherence. That's all. So we just need that information, and that information exists, it's given to you in a density matrix. It's much better than working with wave functions. Okay. Another important thing is something used in quantum optics extensively is a density matrix is particularly useful when you're dealing with some kind of statistical mixtures of quantum states. I don't know if you have come across pure quantum state to mixed quantum states, especially with ever-growing quantum computing and other kind of applications. You need to kind of, you probably would have heard about this. We're not going to talk about much of purity of the states in this major part of the course. Maybe in the later part of the course, we can talk a bit more on the purity of the states and so on and so forth. So there are some properties of density matrices. Of course, rho has to be Hermitian. Trace of rho should be equal to 1 to normalize probability. Of course, this is a big assumption. This is true only for pure state. For what we call as mixed state, which is not pure, your trace can be less than 1. And this is simply basically saying I have a density matrix, but it's mixed with something else. I don't know that, so I'm kind of looking at partial density matrix, and the trace of that will be less than 1 because I'm missing some chunk. Okay. So given that, do we all agree that density matrix is more elegant than wave functions? Right, it's kind of nice. And we also agree that it's good to be in the interaction picture without carrying the baggage. Now we need to find a way to marry these two together, right? And write down the time evolution of the density matrix, right? So now writing out time evolution matrix. Remember definition density matrix. Let's find this out. Side. This H cross H plus H cross H. So I can now write d over dt rho d, very elegant form. Remember this is again rho. Write it as H comma rho. Very powerful. So this is sort of isomorphic to Heisenberg equation of motion, but written for density matrices, and this is referred to sometimes as Liouville von Neumann equation. Right. So now we have not introduced any specific representation. Let's say we are dealing with Heisenberg picture in general. But before that, let me write out one explicitly before we make representation. So if I integrate this, I should be able to say my rho of t is rho of 0 plus I of h cross integral 0 t tau h tau. Looks kind of similar to what we have seen for the wave function, kind of have similar flavor, but now you have that commutator bracket explicitly in the integral. It's kind of an important aspect of it. And since we know, what do we know? We know a lot of things now. We know u, time evolution operator, exponential plus minus I cross rho to t tau of tau can be shown, which I'm not going to do, rho of t is u rho of 0. So again, now we are going to go into representations. So now if I say for a time dependent Hamiltonian in Schrodinger picture, O M T expand it out. Basically, I know that my rho of t is u of 0 dagger. I also know rho of 0 simply sine 0 sine 0, my initial function. Reorganizing this, you will see this will be equal to minus I omega n m t minus t naught rho n m sum t naught. What you will see here in the Schrodinger picture, my diagonal elements rho and n of t will be equal to, looking at this, rho n t naught time invariant. And of course, the off-diagonal elements, the coherences will oscillate at the energy splitting. But my diagonal elements, the probabilities of each occupying each of the state are time invariant. Kind of tells you why Schrodinger picture may not be the most useful one kind of use. Let's kind of write down density matrix in our favorite interaction picture. And recall my wave function in the interaction picture is related to my wave function in Schrodinger picture. The transformation introduced by my time evolution operator of the unperturbed Hamiltonian. So accordingly, my density matrix in interaction picture is given by transformation of similar kind. And you can show my time evolution of my density matrix in the interaction picture is minus I over h cross v I t. Remember, this vi is to the time dependent part of time varying potential. This out, t I of I cool expression. Do we know how to solve such an integral? Did we figure out a way? We did. We were calculating for Tyson series expansion. Use a of repeated substitution of rho I to give a perturbative of your density matrix. I'm using the word perturbative expansion. It's perturbative because you're assuming that the series expansion, kind of. So if I write this out explicitly, my rho sum naught I over h cross t1 t0 plus I h cross integral t naught t2 integral t2 t1 look at the form that is going to kind of emerge. Time ordering is important. I have a nested commutator bracket here. Nested, important and very unique. And I can keep on my most expression, the nth order. Not 1 and very complicated loop. Later on, it will help us developing something very useful. So in general, I can write out my rho I p time evolution density matrix, some zeroth order, first order, second order, so on, order, on and so forth. So this is the nth order expansion of the density matrix. It so happens, this is the momentous thing, big statement, right? So happens that I can relate this with my different chi's. There's something I'm not shown yet, hopefully we'll show. So what we have seen so far, we start out by saying, okay, I need to figure out a way to solve time-dependent Schrodinger equation for situations where my Hamiltonian is time-dependent. That's the thing I started out. And we figured out, we created what's called time evolution operator, which helps you to predict what the wave function is at a certain time t, given its value at certain time t naught. Okay, and we also kind of chose a very specific form of my Hamiltonian, which has a time-independent part h naught and a time-dependent potential. And because my light matter interaction is embedded in that time-dependent potential. So I'm able to write down again the whole thing in the so-called interaction pictures, dropping off the unnecessary flows. Okay. Then we made a huge jump, moving from the so-called wave function to what we call as density matrix, because for the sake of spectroscopy, we don't need to know wave functions. What we need to know is what the probability of finding my particle in a given quantum state, or to identify any presence of coherent superpositions, or what we call as coherences. That's all matter for us. So we are working with density matrix, and I'm able to write the density matrix in my interaction picture, and the time evolution of this density matrix can be perturbatively expanded of this form, where at the heart of it is this nested commutator bracket. Zeroth order, first order, so on and so forth, but it's kind of there. Okay, so now we have to make the next jump. Now we need to understand, okay, what kind of material I have, what kind of electromagnetic field that I'm going to bring in, and how am I going to write my V of t, which will be something that we do in the next class. And then once we have that, then we have all the ingredients to actually start building some experiments. Experiments include linear spectroscopy as well as nonlinear spectroscopy, but we have all the tools at that point. Okay? Okay, thanks.